So, as I just mentioned, this is going to become a very important paper for you. This is actually part of Algebra 2 that I really love this particular section, teaching this section, because for me, this is really what it's all about. The goal for me with this quadratic stuff that we started talking about is to help you understand how it all ties together. And quadratics tie together beautifully. There's a really amazing picture. And the thing is if you look at math books traditionally, quadratics are taught in all these little individual skills in random places, or maybe in one chapter, it's like, here's this skill, here's that skill, do this, do that. But it's rarely ever taught in this big, cohesive, I want you to understand the whole thing and how they all are part of one big picture. And that's what I'm hoping to give you with this next set of lessons that we're going to be working on. And so you can see that you have this big paper and all of these things. And now I've got a couple things scribbled out up there on the paper that you're going to be writing down today. We're going to revisit this paper about 5 times in the next set of lessons. And when you're done, it's going to look something like this right here, okay? And it's going to be worth about 50 points in the homework column. So it needs to be handwritten, kept, clean, and then turned in when we finish the last round of notes. So, my paper losers, if you lose the paper, you're going to have to recopy it by hand. Don't make more work for yourself. Make this a very important paper that you keep track of, and then you only have to write the stuff down one time. Okay? That's the easy way to do it. Make it as painless on yourself as possible. Ready to go? Let's do this. All right. No, we're not writing all this today. That's why I said we're going to revisit this paper about 5 times. Okay? So, let's start with what we've been talking about, which is vertex form. Now, in each one of these circles in this middle section of our paper, we're going to write 2 things. We're going to write 2 functions, one here and one here. So just make sure that you leave some space for those. So for the first function for this, we're going to write the generic version of each of these formats on the top. And so the generic version for our vertex form, as we talked about the other day, is f of x is equal to a, and then it's x minus h group squared plus k. And of course, we know that a can be positive or negative, h can be positive or negative. In the generic format, it's always written x minus h. So if you see x plus h, you know that that came from x minus negative h, which means your graph shifted to the left, correct? Okay. And so this is the generic format of vertex form. Now, I'm not going to give you all of these right now, but the idea here of this paper that I gave you is it's sort of a flow chart. Okay, we're going to start in vertex form, and we're going to flow our way to standard form, which we will talk about today, because today is talking about standard form. And then we're going to flow our way to intercept form, and then we're going to come back from intercept form to standard form, and back from standard form to vertex form, so that you can move fluidly from one form to another. And in each one, there are things that are helpful and easy to find. And then there are things that are still helpful, but maybe a little bit more challenging to find. And so you can do things in different ways. And my goal is to show you all of quadratics. And then I can ask you specific questions in certain ways and say, I want you to do this in this way. All right, that's the idea. Okay, so let's start with some things that we know about our generic vertex form. And so here's where you're going to now do some writing. And I want you to copy this down. And you're going to want to make it fit the way that I've put it here as best to your ability, because like I said, we're going to use a lot of this other space. All the spaces in between, we're going to use those. So make it fit as you see here. Consider yourself like a photocopier. I'll give you a few minutes to work on that. Let's start talking this through a bit. Okay, so let me bring you back to our analogy from early on when we started talking about functions, our introduction to functions. And I said, remember, it's like going to the doctor's office, right? Okay, they get your height, they get your weight, they take your blood pressure, sometimes they take your pulse, maybe they check your oxygen. There's different biometrics that they use to then kind of distinguish you from another patient, and so on and so forth. We are going to have very common biometrics when we talk about these quadratics, okay? And so one of the key pieces of information we need to talk about is, where is the vertex, right? We got to know, where does this graph turn, right? And that way we can talk about maximums and minimums and all this other stuff. So in vertex form, this really is the key piece of information that we pull out of vertex form, is our vertex, right? This is the key piece of information that we pull out. And we talked about the other day when we were looking at our graphs, sliding around, sliding left and sliding right and up and down, that was formed by the H and the K from our vertex form of our equation, okay? Now, let's talk about some other things. I've used this language with you. You're going to get more exposure to it today, this idea of stretching and compressing. Stretching is going to make our graph narrower, while compressing is going to make our graph wider. I just gave you part of it right here, which is this idea that if we're talking about a number that's greater than 1, it's going to cause those y values to stretch up the y-axis, pulling that graph narrower to each other. But it also works the same way. If it's negative, less than -1, it's going to pull that graph narrower down. Okay, so I just gave you the positive versions here. You're going to see all of them and have to choose between them as this comes about. All right, and then of course our compression is our values that either sit between 0 and +1 or -1 and 0. That's compressing when it's facing up or compressing when it's facing down. Natalia, do you have a question?
I was just gonna ask if you should like highlight the different colors and stuff.
Well, I use different colors just to differentiate it. You can, or you don't have to. But I would have you box in, at least highlight this here, because I want to identify that this is the most commonly used and key piece of information that comes from vertex form. We can get all of this from there. All right, now we also talked about the fact that the vertex, right, is h comma k. That's our x and y coordinates. And the axis of symmetry is the vertical line that always passes through the vertex, which means that it always has to pass through the x coordinate of the vertex. So we oftentimes say that the axis of symmetry as an equation for a vertical line is x equals h. Okay, x equals h. So whatever the x coordinate is of your vertex, you know that your vertical line axis of symmetry is going to pass right through that x coordinate. So whatever h is, your vertical equation for AOS is going to be x equals h. Pretty good there? Pretty easy, right? All right, so let's get back to talking about domain and range. Okay, so just by way of reminder, the domain is going to be what are inputs that we can put into the function. Okay? Positive and negative. If we're limited in any sense of inputs that we can drop into the function, then we would have to place a limitation on our domain. Our range, of course, is what outputs could potentially come from our function, positive and negative. All right? Now, the good news about quadratics is I told you they would always open up or always open down, and they're always expanding out to the right and left and expanding out to the right and left, which means that there is no limitation on domains at all for any quadratic. All quadratics will always be domain of all real numbers. That's easy, right? That's a good answer to have. You're just going to have to know how to write that in the proper format, because we're going to use set builder notation, remember that, and we're going to use inequality notation, which is what you see up here, and we're going to use interval notation, and you've used all three of these before, and I'll remind you how to do them today. Okay, so you'll have to pay attention to how the question is asked so that you answer it correctly. Because if I say answer it in interval notation and you give me inequality notation, that will be a markdown. Not a big one, but it'll be a markdown. Okay? All right, now let's talk about range for a second. So since domain is always all real numbers, we don't really need to worry too much about that. Our range, however, does matter, right? Now keep in mind that if our vertex, watch me up here, if our vertex is h this way, okay, or I shouldn't say that, and k this way, yeah, everybody good with me, right? Then the range is going to be determined by the k value. Wherever that vertex sits up and down, that's going to be either the lowest point in the range, yes, or the highest point in the range, yes. And the other side of the range will always be one of the infinities. For a minimum, it will always extend to positive infinity. For a maximum, it will always extend to negative infinity. So you got to find that range point, but then you got to get it positioned in the format in the right place. Now, the vertex is never a hollow dot. It's a solid dot for our vertex, which means that point is always included in our range, which means that it's going to be a less than or greater than or equal to, or a bracket in interval notation. Okay, remember that? Brackets and parentheses, included, not included. It'll come back to you, don't worry. It'll come back to you. So in reviewing this, okay, so when we write a maximum, we're always going to put the smallest value on the left, which would be negative infinity is less than or equal to whatever the k value is. And when we're writing a minimum, we're always going to put the smallest value on the left, so that would be the k value is less than or equal to positive infinity. It's always going to be written like this. If you write it backwards, you will get marked down. Lowest value on the left, read it left to right. Smallest to greatest. Everybody got that? Important you write it correctly. Smallest to greatest. Okay? Anytime we write inequality notation, we're always writing it least number on the left. Least value on the left, moving to the right. Okay? Same thing with our interval notations over here. Right? So for our domain, obviously, for our domain is going to be all real numbers. So in interval notation, we're going to have negative infinity, positive infinity, left to right, and parentheses. Because infinity is a concept, not a value. Okay? For our ranges, if we have a maximum, you see how I have it written with a parenthesis on the negative infinity, but a bracket on the k because it's included at the highest point of the graph. Does that make sense? Okay. And then this here is at the lowest point of the graph, the k value is included, and on up to positive infinity with a parenthesis. Okay? Yes. Everybody good? Yeah. Got the review on domain and range? Right. So let's start with our second line right here. So now we're going to actually take an actual quadratic function in vertex form. So let's write this down. F of x is equal to x minus 2 group squared minus 16. X minus 2 group squared minus 16. All right, here's what I want you to do. Right here, I want you to write A equals and H equals, and we'll fit it in over here, K equals. And I want you to go ahead and fill in the A, H, and K values for this particular quadratic function. Go. Let's take a look, see how you did. These are your A, H, and K values. Okay. You know, I'm going to do it now just to make sure that you're clear on it, but as we move along, you don't need to write that. But I want to make sure that you're clear on the fact that in this case, when you see x minus, your H value is positive, which means your graph is shifting to the right, right? And so, but if it's a negative, you have to write that for sure. Okay? Okay. How are we doing so far? Everybody got vertex form down, right? Okay, so tell me about this particular graph. I'm going to ask you some questions. The questions I'm going to ask you is this graph being stretched or compressed? Do we have a maximum or a minimum? Does the graph open up or down? Talk to your neighbor about the things that we just put up here. What's the domain and range for this particular graph? I'm going to ask you guys these questions in like 30 seconds. Ready, set, go. Okay, so given our function up here, let's do a little quiz time. So I'll start, Quinn, with you. So tell me the vertex of the actual quadratic function, this one right here. What's the vertex?
2, -16.
Very good. The vertex is 2, negative 16. Of course, vertex is H and K, so if you can pull out the H and K, you can write it as an ordered pair. All right. Jane, do we have a minimum or a maximum? How do you know we have a minimum? Because what's positive? Because A is positive, and so then, Lauren, does our graph open up or open down? Okay, it opens up. Good. All right, so we got one of these going on, right? Okay. All right. Gio, is our graph being reflected, stretched, or compressed? And how do you know?
Reflected.
Being reflected. Why would you say that?
Because
Okay, so reflected would be flipped upside down.
it's neither.
So then it's none, right? It's not being reflected. Is it being stretched or compressed? No. Right. So if A is positive 1, then it's not being reflected, stretched, or compressed. Right? Okay, so that's the language that we want to get used to seeing. All right, good. Okay. Let's see. Andrew, what is the domain for this particular function? All real numbers. Very good. Very good. And Fisher, what is the range for this function? -16, comma, infinity. Okay, how would you write that? If you're going to say it like that in interval notation, give me some symbols to go along with that. Like, how would you encase that then?
So bracket -16, comma, infinity.
Very good. Okay, yeah. Or to put it in sort of, that's very mathy language, but that's correct. But to put it in just kind of like layman's terms, we would say it's all of the numbers greater than or equal to -16. So our range sits at, okay, watch me. I'm at 0, 0 right now. You ready? Okay. So I'm going to go to -16, right? And then the graph's going to be drawn with a parent pattern of 1, 1, 2, 4, 3, 9 because I don't have any stretch, compression, or reflection going on. Okay? So it's going to sit below the x-axis, right? And so my range is going to be all of the numbers greater than -16. Now think about that picture for a second. The graph is not drawn anywhere below -16. That's why the range starts at -16 and goes to positive infinity. Does that make sense? Okay? That would be the minimum. That would be the lowest point on the graph. Okay. All right, good. Okay then, let's go with, we've talked about vertex form. We've got a good feel for how these work. Let's talk about now standard form or general form. This is referred to as both. Ready? Here we go. Again, 2 lines. We're going to write 2 different lines here. We're going to write the generic form first, and then we're actually going to take this same quadratic that we're working with, and we're actually going to do this math with this quadratic all the way through, okay? So we're going to keep the same problem, and you're going to see how that works. All right, so here's our standard or generic form of a quadratic function. It's f of x is equal to ax squared plus bx plus c. No, we're not doing Pythagorean theorem. All right, now we're gonna write something down that I'm gonna tell you about now, but it's gonna become really important later on. Okay, so right here, I want you to write decreasing degree. Decreasing degree. Decreasing degree. What that means is when we write our quadratic functions, or for this matter later on down the road, our polynomial functions, in order of decreasing degree, that means we write the biggest exponent first, and then we work our way down to the bottom. So the biggest exponent is to the second. The next biggest exponent is to the first. This is x to the 0, which is 1, which means that there's no variable. Well, no. C is always a constant. Okay? So in a quadratic, it's going to go to the second, to the first, and then constant. Okay? All right. So then let's talk about how do we get from vertex form to standard form. So the way we do that is we're going to simplify the input side. We're going to simplify the input side of our vertex form quadratic function. All right, now I want you to give yourself just a little separating squiggle right here. Okay, and we're gonna write our vertex form of our actual function we're working with, which is f of x is equal to x minus 2 group squared minus 16. Okay, and we are going to simplify this side of the equation. Simplify, again, means do math till you can't do no more math. That's what simplify means. Do math till you can't do no more math. Okay. Go. Well, no, when we're simplifying, we always kind of simplify down. Here, I'll give you a hint. The first math problem that you need to do is that. That's the first thing you need to do. And maybe it might be helpful for you if you did that like this.
No. Wait, what?
You know, like this.
We don't fill in the H2H.
Huh? That's what that's for. Put in H and K. H and K are already there. This is H. This is K.
It's not what we were doing yesterday.
No, we're not plugging anything in. We're simplifying. Plugging in is evaluate. We're simplifying. Difference between run to the fence and hop to the fence.
I understand.
Okay. All right. Let's see what you do with that. Okay. If you did your math correctly, it should have looked like this.
Yes.
Right? Because, again, I'm taking x minus 2 group and I'm multiplying it by itself. X minus 2 group times x minus 2 group. Don't miss the common terms in the middle. Binomials squared are going to produce trinomials. Okay, we did this in Algebra 1. You should have done this in Algebra 1. You should have done this in Algebra 1. Okay, wow. Shh, this is on tape. Don't say that out loud. I was not their Algebra 1 teacher, for the record. Just want to make sure I'm clear about that.
It's a girl.
What's a girl? The baby or the teacher? I'm confused now. I'm lost. I don't understand.
Do you not remember Miss Robinson?
No, I don't.
No, I was like, what?
Okay. Well, good for her. That's awesome. Okay, we got to keep going. Happy for Miss Robinson, but we're moving on. All right. Next up, you got to continue to simplify, combining like terms. Okay, so plus 4 minus 16? Negative 12. Question, do you have any more like terms you can combine together here? Then you've done math until you can't do no more math. That means you're simplified. Which means that standard form of this equation is x squared minus 4x minus 12. Okay, take a look up here. Here is the red graph is your f of x equals x minus 2 group squared minus 16. That is your vertex form of the function we started with. Here's the standard form of the function we came up with. It is in blue. Check it out. It's the exact same function because all we did was just do a little math to the side. Okay, same function. We just simplified the input side of our vertex form, and so we just changed the look of it. Changed its shirt. Same function, just changed the look. Like 1/2, 3/6, and 4/8 all look different and all would be the same amount filling if they were pizzas you were eating. It's a great question that's not for today. But I love the thinking, Pierce. Is a fantastic question. And yes, we will talk about all of that. But to answer your question, Pierce, to answer your question just in really short, every quadratic function can be written in vertex standard, well, and not necessarily intercept form, but vertex and standard form. Okay? Every quadratic function can be. Well, he was asking, can only certain quadratics be written in vertex form? Okay. But every quadratic is going to have a vertex, so every quadratic could be written in vertex form. And every vertex form can be written in standard form. Now, how to write it in intercept form, that's a whole different story. We'll talk about that another day. Okay, here is the lesson you are looking for on formative. Don't cry yet. It's not that bad. They're multi-part questions like, what's the vertex? That's an easy question. That should take you like 5 seconds to answer. Don't fret. Don't fret. Hey, you know what? You can be joyous in your sufferings. Okay, all right. You ready? Let's do this. Okay, so first thing we're going to do, here we go. You ready? Is we are going to practice converting to standard form. So in this section of questions, you're going to be converting your quadratic functions in vertex form to standard form. You guys just have the instructions on your screen right now, right? Okay, all right. Okay, so first one is here. You're converting this function, f of x is equal to x plus 3 groups squared minus 4. You're converting that to standard form and showing your work as you do that. The work should look a lot like what I just showed you over there. You don't have to write out the box multiplication. If you know how to multiply binomials and you can do it correctly, you do not need to write that out. If you do write that out, please write it off to the side. It is scratch work, just like if you were doing something with, adding or subtracting scratch work, okay? Okay, just real quick, here's what you should have come up with. X squared plus 6x plus 5. Again, positive 3x, positive 3x. So that's what you should have put together. All right, you are converting to standard form. Okay, here's your correct answer here. G of x is equal to x squared minus 8x plus 19. Okay, now we're going to skip it up a notch. So do you do multiplication first or do you do exponents first? Then you need to square before multiplying. Which is the most common mistake that's made when you have an A value is you want to distribute it first, but you don't distribute it first because that's multiplication. You have to process exponents first. So make sure you square the x plus 4 group first. Then you can multiply by the negative. Okay, so I've said it a couple times, but this is what you're supposed to do here, right? You expand out your x plus 4 group squared. You distribute your negative. You can see the negative needs to be distributed here, and then you can combine your like terms. Okay, got another one. Let's see what you do with this one. Go for it. Converting to standard form. You are literally correct. Here's what you should have come up with for this one, right? So again, you're going to expand out your x minus 5 group squared. Then you take your 2 and you distribute it over the top. So your A value is being multiplied out over the top here. And then you simplify your like terms to come up with your answer. All right, I got one more that I want you to do. What's life like without having to do some fractions? Here we go. Okay, let's take a look and see how you did. This is what you should have come up with for your answer. Again, expanding out your squared group and then distributing your 1/2 and then finally combining your like terms. Okay. All right, so we are now talking about standard form, right? And so we had some key things that we were looking at in vertex form, specifically our A, our H, and our K, right? And these were controls that shifted our graph. Now, standard form is a little bit different. There are some key values that we're looking for, but they are not the values that we use to shift the graph left, right, or reflect it, or stretch it, or compress it. That's in vertex form. This is a different format. And so the key values that we're looking for in standard form are A, B, and C. So what I want you to do right now is I want you to see if you can figure out what the A, B, and C values are from our actual quadratic function, the one that we just saw that we converted from vertex form to standard form. Go ahead. Here's what you should have put for your A, B, and C. Okay? So just like looking for A, H, and K in vertex form, when we're in standard form, I'm going to ask you for A, B, and C. Now, here's the good news. The A value is the A value is the A value. In all three formats, the A value means the same thing. Now, this is important, right? Because I want you to think about something for a second. Gio. This is important because in vertex form, if our A value is greater than 1, we know that we're getting stretched upward, right? We know that if our A value is negative, we're getting reflected, right? We also know that that controls compression and stretch in both directions. It's the same thing in standard form. You're reading the same reflection, stretch, compression off of this A value as you are off of this A value. Do you understand that? Because I'm going to give you a bunch of questions in standard form today, and I'm going to ask you, is the graph of this being stretched, reflected, compressed, and how do you know? And the answer is going to remain the same as in vertex form. It's because of the A value and what you know about it. Does that make sense? Yeah. Okay. Now, the B and the C come into play in a different way, and so we're going to kind of look at that right now. So we're going to copy some more notes down. Now, this is what we're going to start with, but you can see that I have more to talk about at a later time. So let's just start with this for now, and then we will come back and talk about it. All right, so in vertex form, I made the case that one of the most helpful, easiest biometrics we can pull is the vertex. That's what vertex form is all about. Well, in standard form, probably the easiest biometric that we can pull is the y-intercept. Let's box in the y-intercept. Oh, thank you. The y-intercept. All right, now, y-intercept is where our quadratic crosses the y-axis. Got that? So we got this parabola that's either opening up or opening down, and somehow as it extends to the left or the right, at some point, it's going to cross the y-axis because it's always extending to the left and to the right. So at some point, it's always going to reach the y-axis. Now, in standard form, this is really easy for us to find because if you think about any y-intercept, any point along the y-axis here, like that, is always going to have an x value of 0. In other words, an input of 0. So if I were to take a standard form function, like, say, this one right here, and I were to plug in a 0 here, what's 0 squared? 0. And then what's negative 4 times 0? 0. So then that's why this is always the y-intercept. Kind of like y equals mx plus b. No way. But it's a different b. It's now c. Get the idea? Okay. For the same reason, though, because the input is 0 for all y-intercepts. Again, for any point along the y-axis is always going to have an x of 0. That's going to leave this as the y-intercept. Now, when you write it as an ordered pair, you're going to write it 0, negative 12. Make sense?
Yeah.
Okay. Yeah, because that's what we're doing, input output. Okay. Now, great. I need you to focus and not be talking. All right, now let's talk about this weird looking thing right here. Now keep in mind from our vertex format, right? We said that the axis of symmetry is x equals h. Okay, x equals h. And h is the x coordinate of our vertex. That's where that vertical line comes down and goes through our vertex, right? Well, when we're looking in standard form, we have this cool little formula that works for us here, where we take negative b and we divide it by 2 times a. This is our a and b from down here. And that's going to get us the axis of symmetry for our standard form quadratic function. So in other words, for this one, our axis of symmetry, let's just do this like here, just without writing anything out. You can do this, it's easy. Okay, so what's negative 4? Positive 4, right? Okay, and then what's 2 times a? 2. So what's 4 divided by 2? So your axis of symmetry for this function is x equals 2. See how that worked? That was easy, right?
So if it's a negative, then you're taking the negative.
Because it's negative b. So if your b term is negative, then it's negative a negative. The opposite of a negative. Okay? Focus. Okay, now listen. Okay, this is where it gets a little tricky. Watch this. Remember the vertex is, well, okay, the axis of symmetry is always x equals h, right? And the vertex is always h equals, or h comma k, right? So then when we find this, we find this. And we know that the vertex must be on the graph of the function, which means that this h comma k, which this is now positive 2 for us for our example, right, is a verified input-output of our graph. So then if we know the input and we know the equation, we can find the output. And that's what we're going to do. We're going to use our h, our input, to find our k. And so what you're going to do for these is you're going to take your input. You ready? We're going to do this together right here. So our x value of our coordinate is what? Of our vertex? What did we just say it was? 2. So what's 2 squared? Okay. What's negative 4 times 2? Okay. So now we've got 4 minus 8, which is what? 4, negative 4 minus 8. Negative 12, right? Okay. So because this is positive 4. Sorry. Positive 4 and negative 8. So it's negative 4. Yeah, negative 4. Yeah, that's right. Negative 4. Right. Okay, negative 4. Sorry, my bad. Okay, and then negative 4 minus 12 is negative 16. So that means that the vertex for this function is what? Vertex. It's a point. 2 comma negative 16. What's the vertex for the function? 2 comma negative 16, right there. See it? Okay. So that's what we're going to be doing today, and we're going to do one question together. So back to formative. Okay. By the way, real quick, I'm going to leave you with one more converting from vertex form to standard form to do as part of your homework. So you're going to have one more to do here. So again, your job is to complete this formative, okay? Okay, so what you should be now looking at, oh, I need to unpause you, don't I? Okay, here we go. All right, now you should be looking at this question right here. All right. It's really not that tough, okay? Let's start working our way through. I want you to do 7A, I want you to do 7b, write your y-intercept as an ordered pair. And then I want you to try to answer 7c and d. And then stop when you get to 7e. We're going to talk about that together.
Mr. Burgess, they aren't on partial credit. You have to get them all right. So sad.
You don't get partial credit for the question?
But once you put them all right,
So it doesn't give you 1 out of 3, 2 out of 3, 3 out of 3.
It just gives you 0.
But it does give you 3 out of 3 when you get there. Okay, all right, that's good to know.
But yesterday it was doing like the partial credit was this thing.
We wrote the functions for you in the show your work section. So this is where you're going to find your A, B's, and C's, and then you're going to find your axis of symmetry. Now remember, that's x equals h, and in standard form, h is found using negative b over 2a. So I want you to write your axis of symmetry using your negative b over 2a for this function. So when you're ready to tackle 7f, to find your vertex, now that you know what your h is, right, you're going to plug that in to your function and find the output that partners with the h input. And then you just do domain and range. Pay attention on the domain and range so that you put it in the right format. I have for the first question all 3 formats so that you can practice doing set builder and interval and inequality. But on the other questions, I just picked one of them. So make sure you read the question carefully, all right? So complete this formative is your homework. This is a really important homework assignment. Please don't blow this off, all right? Okay? You should be able to do this. It's not that long, okay? Have a good day.